Yesterday we defined a new term called momentum. There was two ways that we defined it. What was one of those ways? The everyday way or the technical way? I don't really care. Okay, so it's the product of an object's mass and velocity. That's the real definition for momentum. That's good. The product of an object's mass and velocity, which takes us to an equation, P is equal to m times v. But what's the other way we define it? Kind of the everyday understanding of it, Emily? Yeah, it's how hard it is to stop an object. Now, the second definition, P is equal to m times v, the real definition, kind of comes from the first everyday understanding of it, how hard it is to stop something. The reason being, the harder or the more mass you have in an object, the harder it is to stop. Bigger mass, harder it is to stop, right? Semi-truck is harder to stop than a little smart car is because it has more mass. But the velocity of the object determines how hard it is to stop the object as well. The faster the smart car is moving, the harder it is to stop the smart car. So mass and velocity both positively affect the amount of momentum that an object has. M is in mass, of course. What units should we measure mass in? It's going to be kilograms, right? What units should we measure? What's this term? Velocity. What units should we measure velocity in? Good, meters per second. And of course momentum, P with the little arrow over it, is momentum, and it's going to be measured in what units? Good, kilograms times meters per second. Is mass a vector or a scalar? In other words, there is no direction associated with it. Good, it's a scalar, no direction associated with it. What about velocity? It's a vector, momentum is a vector, right? We have a little cheat here, right? We have our data sheet that has this equation written on there, and on the data sheet it tells you whether it's a vector or a scalar by virtue of whether or not there is a little half arrow over top of it. If you forget that velocity is a vector, look at your data sheet. It tells you. You see the little half arrow, it's a vector. You don't see the half arrow, it's a scalar. All right, momentum is clearly dependent upon mass and velocity. Inertia, on the other hand, which is real similar to momentum but not the same thing, depends upon what? It just depends upon mass, right? So an object that's at rest will have just as much inertia as an object that's moving down the road, but an object that's at rest doesn't have any momentum, whereas the object moving down the road does. Inertia is the tendency to resist any change in motion. If it's at rest, it wants to stay there. If it's moving, it wants to stay there at a constant speed or constant velocity. Okay, but momentum, on the other hand, is just how hard it is to stop something. It's got to be moving in order to make it difficult to stop something. Got it? Okay, we don't use inertia a whole lot in Physics 30. Okay, we focus on momentum, of course. That's our unit, right, is momentum and impulse. But we want to distinguish between momentum and inertia just so that when we hear those terms, we know the difference. Yep? We had worksheet number 1 for homework last night. We did the first handful of questions in class, but we assigned the rest of it for homework last night. Let's take a look at 6, 7, and 8 on that worksheet, starting with number 6. It says a 2.00 kilogram rock is dropped from rest from the top of a 30-meter high building. Calculate the ball's momentum at the time that it strikes the ground. So this is real similar to that example question that we had in our notes. We can see that our mass is 2.00 kilograms here. We can see that VI is 0 meters per second because it's dropped from rest. If it was thrown down at a certain speed, we'd say VI is something, right? But here, because it's dropped from rest, VI is 0. My displacement is what? My displacement is negative 30, right? Because it's 30 meters below where I started. We're looking for the momentum as it strikes the ground. To find the momentum as it strikes the ground, we're going to first get the velocity. And I think I'm going to use VF squared is equal to VI squared plus 2AD to find that. And then I'm going to use P is equal to M times V. So let's say VF squared is equal to, hey, why did I put that X through that? Because it's 0, yeah. So VF squared, or let's just say VF is equal to the square root of 2AD, which is the square root of 2 times negative 9.81 times negative 30. And that final speed is 24.26 108 meters per second. Is that all right? Now you want to find the momentum as it strikes the ground. We know the velocity. Oh wait, no we don't. What do we know? We know the speed as it strikes the ground. We need the velocity as it strikes the ground to get the momentum. What's the velocity? Yeah, it's just negative 24. Let's say P is equal to m times v. It's 2.00 times negative 24.26108, which gives me a momentum of negative 48.5 kilograms meters per second. I'm going to leave it like that, negative 48.5, but you could have absolutely dropped the negative and made it, just wrote the word in, 48.5 down. All right, is that good? 7 gets a little harder here. 7 says a 1 kilogram rock is thrown up into the air from ground level at a speed of 8 meters per second. The ball travels up to a maximum height and then returns down to the ground. We want to find the momentum as it strikes the ground. So it's similar, but yet a little bit harder, I think. Okay, let's in our minds describe what's going on here. As this rock is thrown up into the air, like, with an initial speed of 8 meters per second, what happens to it? Like, what happens to the rock as it moves up? It slows down. At what rate does it slow down? Good. It slows down at 9.81 meters per second squared. And at some point, what happens to that rock? It stops. Not for long, like for one instant in time. What does it do after it stops? It starts speeding up, downwards. At what rate? Negative 9.81. So let's get this straight. We start off at 8 meters per second. Okay, initial speed of 8. We slow down at 9.81, and then we stop. And then we speed up at 9.81. What's our final speed going to be? If we start off at 8, and then we slow down at a certain rate, and then we speed up at the same rate over the same distance, our final speed is going to be the same as the initial, right? 8 meters per second. How many people caught that little shortcut on that question? Okay, good. If you didn't, that's okay, because there's a way to deal with this mathematically as well. We could say, analyzing the whole trip up and down, we could say VF is equal to the square root of 8 squared, the initial speed, plus 2 times negative 9.81, because the acceleration over the whole trip is negative 9.81, times, what's my displacement? Over the entire trip? 0, because I end up where I start, right? So that makes my final speed 8 meters per second. Go figure. Okay, lots of us figure that out just logically, but mathematically, go figure, it works out to be the same value. It doesn't really matter how you figure that out. Okay, there's always a math way, but sometimes we can logically figure it out as well. Okay, now the question becomes just like number 6. We're going to say P is equal to m times v, which is, in this case, 1 kilogram times negative 8, negative because it's downward. That gives us negative 8.0 kilograms meters per second. Or we could have said positive 8 down. Good? Okay, number 8 looks similar again, but yet a little bit different. A 1.5 kilogram rock is thrown up into the air from ground level, reaches a max height of 7, and returns to the ground. What's the momentum as it strikes the ground? We don't know what the initial speed is like we did in question number 7. But we do know the max height here. If we try using this equation with a displacement of 0, we got a problem. If we're analyzing the whole trip like we did in question 7, our problem is that we don't know what VI is. So what do you suggest we do? Yeah? Oh, you want to do an energy thing. So energy potential equals, okay, so you're saying the energy at the top equals the energy at the bottom? Yeah, that'll work. Okay, mgh equals 1/2 mv squared. Absolutely, that'll work. So will this equation if we analyze like you just did, the trip down. So instead of doing this, let's analyze just this, the trip down. Okay, if we analyze the trip down, what's VI? 0, because it stopped up there, right? So let's do that. Let's analyze just the trip down. Vf squared is equal to Vi squared plus 2AD. Let's cross off Vi, because it's 0. Vf becomes the square root of 2 times neg 9.81. What's my displacement? If we're analyzing just the trip down, it's -7, not 0, right? If we're analyzing the whole trip, it's 0, but we have too many unknowns for that. So let's analyze half the trip and see what that gets us. When we do, Vf works out to be 11.71921. And now, just like question 6 and 7 now, right? Now it's P is equal to m times V, which is, well, 1.50 kilograms times negative 11.71921 gives us negative 17.6 kilograms meters per second. Or we could say 17.6 kilograms meters per second down. Okay, either way is fine. A lot of times on a test, we're actually asked for the magnitude of the momentum, and we don't even need the direction. But we want to be ready with the direction just in case. Because they don't always ask for the magnitude. Sometimes they ask for the momentum. Be ready just in case. Let's take a look at another example on topic 12 now. This one's going to be 3b. We finished up 3a yesterday, and when we did that, we found the momentum in question 3a to be negative 4.4 times 10 to the 3 kilograms meters per second. And we found the kinetic energy in question number 3a to be, what was it, 1.4 times 10 to the 5 joules. What was the big difference in the way we were thinking about kinetic energy versus momentum here? Clearly the equation, right? M times V versus 1/2 mv squared. But beyond that, what was the big difference between kinetic energy and momentum? Yep. Good. When we calculated kinetic energy, we didn't pay any attention whatsoever to direction. One of these was south, one of these was north. Okay, positive, negative, doesn't matter. Kinetic energy is a scalar, speed's a scalar. We just drop any reference to direction whatsoever when we're calculating kinetic energy. But for momentum, we had to include the north and the south. So we calculated the momentum of the first one. It was positive. The momentum of the second one was negative. When we combined those, we obviously got negative 4.4. Okay, let's take a look at question B now. Same scenario, except this time the car is traveling north and the truck is traveling west this time. So let's see what we can do here. Let's draw a picture to try to set this up here. Let's say the car that has a mass of 1,000 kilograms has a velocity of 10 meters per second. The truck has a mass of 1,200 kilograms and a velocity of 12 meters per second to the west. Let's get the momentum of the truck. That's easy, right? 1,200 times 12 is 14,400. And the momentum of this car is 10 times 1,000, which is a nice, easy round number, 10,000 kilograms meters per second. What's the momentum of this system? Now the car and the truck combined, 14,400 plus 10,000, 24,400, is that right? That's wrong. If I was to say 24,400, clearly I've just added those two together, right? Why is that wrong? What's wrong with that? What is it? It is at an angle, but like, take a step back from that for a second here. Yeah? You're not taking into account the direction. The final answer does require an angle because you have to take into account the direction. And if we just add those 14,400 plus 10,000, 24,400, we haven't done that. We haven't taken into account the direction. So how do I take into account the direction here? In question A, all I did was said, one is positive, one is negative, add them up. Here I got to add them up, but I got to add them up in a different way. How do you suggest I do that? How do I add those two numbers up? Yeah? Yeah. I want to find the resultant vector. I want to find the Pythagorean theorem. I'm going to say P is equal to 14,400 squared plus 10,000 squared equals, we square root that, it equals 1.8 times 10 to the 4 kilograms meters per second. And because momentum is a vector, we also need a direction. Theta here, theta, my direction, is going to be the inverse tan function of opposite, which is 14,400, over adjacent, which is 10,000, gives me an angle of 55 degrees. And that would be 55 degrees west of north because of where I have the angle drawn. Had I drawn it like this, then my angle would have been, what, 35 degrees north of west, which would have been fine, right? This is just consistent with the way that I drew it. Does that make sense? All right. What about kinetic energy? What's the kinetic energy? How am I going to go about doing that? Yeah, Marcus? Yeah, same as the first one. 1.4 times 10 to the 5 joules, because kinetic energy is a scalar. The numbers were the same in question A and B. It's just the directions were different, right? Kinetic energy doesn't depend upon direction, so that means that the answer is going to be exactly the same. Does that make sense? So keep that straight, please. When you're using a vector, you got to take into account positive and negative, as you did in A, or components, x and y, like you did in B. But when you're dealing with kinetic energy or any other scalar, then the directions, signs, angles, x, y, completely irrelevant. Just add them up in the same way regardless. Is that okay? All right, I want to do one more example here, which is quite a bit different actually than question number 3. The next example that I want to do is number 4. It's on the bottom of your handout that you got yesterday. It says the momentum of an object is 200 kilograms meters per second. What's the momentum become if the mass is doubled, but the velocity is reduced to 1/3 of its original value? So let me get this straight here. We're being asked to find the momentum, what the new momentum becomes, without knowing what mass is or what velocity is. We just know what we changed it by. Well, here's our general strategy for a question like this. I call this the technique that we use to solve this. I call it variable value changing. We're changing the value of variables without knowing what the variables were to begin with. Variable value changing. And the general strategy is actually quite straightforward. What we'd have to do is write down a relevant equation. If I was solving this question with numbers, what equation would I use? That's easy. If I had numbers and I wanted to find momentum, what would I use? P is equal to m times v. So write that down. P is equal to m times v. Now I'm going to make a little confession. I lied to you about something yesterday. Yesterday I told you the equation, well, and I just did too, the equation for momentum is m times v. That's not true. The equation for momentum is not m times v. The equation for momentum is mass times velocity. Those are just symbols that we chose to represent mass and velocity. Does that make sense? We could have called velocity q. Then what would the equation look like? m times q, right? We're just representing velocity by v and mass by m. Make sense? And that's okay. We can do that all the time. But you're going to see in a second that the way that we're representing it becomes important. Okay, this is my equation. I'm going to put a little subscript O there. That means my original value. This is what it is when I start. Equal to m times v. And we know the original value numerically is 200 kilograms meters per second. Nothing groundbreaking there, nothing earth-shattering. We've just written down an equation that they tell me on my data sheet, and we've written down a number that they tell me in the question. So we just know that when I start, the momentum is m times v, and when I start, the momentum is 200. But what does it become? What does it become? What's my new momentum? Well, now it comes time to change the symbol. Instead of m, my new mass, it's still mass times velocity, right? But my new mass isn't m anymore. Anybody want to take a stab at what my new mass is? It's 2m, right? That's my new symbol for momentum, for mass. It's 2m. The symbol was m, now the symbol is 2m. What's the symbol now that we're going to use for velocity? It's 1/3 of v. Instead of v, it's 1/3 v. Here's a question for you, Jackson. Asking you because I know you're going to know the answer to this one. What's 1 times 2?
2.
Good job. Did you notice he didn't even pull out his calculator for that? He just did it. That's why I asked him, because I knew how smart he was. Emily, what's 2 times 1? Good. So 1 times 2 is 2, 2 times 1 is 2. It doesn't matter what order we multiply numbers in, right? I forget what property of math that's called. What's it called? Sorry? Commutativity? Can't even say the word. I can't even say the word. Let alone remember what the word is. Doesn't matter what order we multiply the numbers in, right? It doesn't matter what order we multiply these in either. 2 times m times 1/3 times v, or 2 times 1/3 times m times v. Same thing, right? Let's simplify it a little bit, actually. 2 times 1/3 is 2/3 times m times v. You agree that that's the same thing? We're just trying to simplify it a little bit, right? Really, what we're trying to do is get mv together because we know the value of mv. It's 200. Right? We know it's 200. They told me that. So we're going to say the new momentum is 2/3 times 200, which works out to be 133. So without knowing what the mass was or what the velocity was, just knowing what they changed by, I was able to determine that the new momentum is 133 kilograms meters per second. Does that make sense? Yep. Could you have given values for m and v and come up with the same answers? Yes, you could have. Okay, but there's a danger in that. Okay, there's a danger in arbitrarily subbing numbers in for values of things that are not correct. In some situations that works for us, but I would hesitate to do that because that won't work for us in all situations. It would here, okay, but it wouldn't in all situations. So I would just generally say, let's not sub in random numbers for things, okay, because that won't work in all types of problems. All right, I don't have any of these on your worksheet, but I do have one on the board here right now. I'd like you to just take a look at this question and see what you can do over the next 2 minutes with this question. All right, so the velocity of our car is 20 meters per second. We want to know what the velocity would be if the momentum was half of its original value and the mass was 2/3 of its original value. What equation is my relevant equation? If I was solving this with numbers, what equation would I use? P is equal to m times v, right? P is equal to m times v. But in this case, I actually have to rearrange it because I'm solving for velocity, right? Right? So what's it going to be? Yeah, velocity is equal to p divided by m. This is my original velocity, and that's equal to 20 meters per second. Good? All right, what's my new velocity become? My new velocity is equal to, well, it's momentum over mass, right? But what's momentum now? What's my symbol for momentum? 1/2 p, not p, but 1/2 p. What's my symbol for mass? 2/3 of the mass. Ooh, dividing by fractions. You guys remember how to divide by fractions? Yeah, you multiply by the reciprocal. 1/2 times 3/2. Right? You guys remember that? Dividing by a fraction, multiply by the reciprocal. Flip it over and then multiply by that. Don't forget the p over m. 1/2 times 3/2 times p over m. We can simplify this. Combine 1/2 times 3/2. We get 3/4. Right? 1 times 3 is 3. 2 times 2 is 4. P over m. Oh, look at this. We know what p over m is. P over m is 20. So it's going to be 3/4 times 20, which is 15 kilograms meters per second. How's that? How many people got 15 for that? Okay, does everybody know where they messed up on it if you didn't get 15? Good?